Welcome back, dear friend. Tonight, we'll be traveling through time itself, exploring the vast and wondrous story of our planet, the entire history of Earth, from its fiery beginnings more than 4.5 billion years ago, to the rise of oceans, the dance of continents, the birth of life, and the unfolding saga that eventually brings us to the present day. So before you get too comfortable, take a moment to like and subscribe, but only if you enjoy the kind of content that blends myth with mystery. And let us know in the comments, where are you watching from and what time is it for you right now? Sometimes these stories are better than sleep, and other times they make you dream louder. It's time now to dim the lights, turn on a fan for some soft noise, and let's cover what we have for tonight together. Close your eyes for a moment and imagine drifting back, not just hundreds of years, not even thousands, but billions. Imagine traveling backward so far that the world beneath your feet vanishes. The continents retreat into a glowing ball, and then even that dissolves into clouds of dust and gas. You are floating now in the depths of space, and the story of Earth has not yet begun. Instead, we are at the beginning of something far greater, the birth of an entire solar system. Roughly 4.6 billion years ago, the galaxy was quiet, at least in this small corner of the Milky Way. But silence in space is never truly empty. Between the stars, immense clouds of gas and dust drifted, remnants of generations of stars that had lived, exploded, and scattered their ashes across the cosmos. These ashes were not lifeless. They were seeds, rich with carbon, oxygen, silicon, iron, and countless other elements forged in the hearts of ancient suns. In one such cloud, something began to stir. Perhaps it was the shock wave of a nearby supernova, the dying gasp of a massive star. Perhaps it was simply the quiet work of gravity, drawing tiny motes together until they could no longer resist falling inward. Whatever the cause, the great cloud of gas and dust, what astronomers call a nebula, began to collapse. As it did, it spun. This is a rule of nature, like a skater pulling in their arms to spin faster. The collapsing nebula whirled itself into a flattened disk, swirling around a glowing center. In that center, matter collected so densely and pressure grew so fierce that nuclear fire sparked to life. Our sun was born, igniting with the light that still warms your skin today. The sun's birth was not quiet. It blasted the newborn system with fierce winds of charged particles, sweeping lighter gases outward, shaping the architecture of what would become the planets. Near the sun, where the heat was searing, only metals and rocks could remain solid. Farther away, where the cold ruled, ice could survive. This difference would determine which planets became small and rocky, like Mercury, Venus, Earth, and Mars, and which became vast and gaseous, like Jupiter and Saturn. But Earth did not exist yet, not even as a full planet. Instead, in that whirling disk of debris, grains of dust collided, stuck together, and grew. These tiny collisions happened millions upon millions of times, like raindrops merging into puddles. Dust became pebbles, pebbles became boulders, and boulders became planetesimals, small worlds, some only kilometers across. The process was not gentle. Every moment was filled with impacts. Imagine a chaotic ballet of thousands of miniature worlds, colliding, breaking apart, and fusing together again. Some were flung away, ejected into the outer solar system or into the void of interstellar space. Others merged into larger and larger bodies, pulled together by gravity's relentless tug. Slowly, a handful of these growing planetesimals claimed the lion's share of the matter in their orbits. These were the embryos of planets, and among them, Earth began to take shape. At this stage, the young proto-Earth was hardly recognizable. It was small compared to the world we know today, a glowing ball of molten rock bombarded constantly by asteroids. Each impact added mass, but also heat. The surface churned like boiling soup. The sky was a haze of vaporized stone and gas, and nothing resembling life could possibly exist. Yet, in this chaos, the foundation of everything we are was being laid. The early solar system was dangerous. Vast objects roamed freely, crossing paths with the forming planets. One of the most dramatic encounters came when a Mars-sized body, which we now call Theia, smashed into the proto-Earth. The collision was catastrophic, so powerful it nearly destroyed our world. Mountains of molten rock splashed into orbit, forming a glowing ring around Earth. Over time, that ring gathered into a single companion, the Moon. The creation of the Moon was more than just a violent accident. It was a blessing. Without it, Earth's spin might have wobbled chaotically, its climate veering wildly between extremes. But with the Moon's steady gravitational hand, Earth found balance. Tides were born, cycles began, and the seeds of habitability were secured. Meanwhile, the other planets found their places. Mercury, closest to the Sun, was scorched and barren. Venus, wrapped in a heavy cloak of carbon dioxide, would later become a furnace. Mars, smaller and lighter, would lose much of its atmosphere, turning cold and dry. Beyond them, the giants Jupiter and Saturn swept up vast amounts of hydrogen and helium, becoming titans, while Uranus and Neptune circled even farther out, their blue-green ices shimmering in the dark. Among these worlds, Earth stood as something of a miracle, at just the right distance from the Sun, in what scientists call the habitable zone. Earth had the potential to hold liquid water. Its mass was large enough to cling to an atmosphere, but not so massive as to trap choking gases like Jupiter. Piece by piece, as billions of years passed, Earth was assembling the conditions that would one day welcome life. But in these earliest days, the world was still raw and molten. The young sun shone more faintly than it does today, giving off perhaps 70% of its current light. Yet volcanoes on Earth belched gases into the sky, forming a primitive atmosphere that held enough heat to keep the planet from freezing solid. And through it all, the solar system slowly settled. The chaos of impacts dwindled as the last large bodies either merged into planets or were swept away. The great bombardment would continue for hundreds of millions of years. But compared to the violent beginning, the stage was slowly clearing. The planets circled the sun in their new orbits, stable and enduring. When you look at the night sky today, you can still see echoes of this time. The craters on the moon are scars of those ancient impacts. The asteroids that drift between Mars and Jupiter are leftovers, fragments that never quite joined a planet. The comets that sail in from the outer reaches carry the same ices and dust that once rained down on Earth, perhaps even delivering the water that fills our oceans. This is the deep beginning of our story. Before there was Earth as we know it, before there were continents, seas, or even the faintest stirrings of life, there was a nebula collapsing, a star igniting, and a disk of dust and gas whirling into planets. In that disk, our world began, forged from cosmic debris, shaped by collisions, and steadied by a moon born in fire. And so, as you drift further into sleep, remember, every breath you take, every drop of water you drink, every stone beneath your feet, all of it comes from that ancient nebula. We are, in the truest sense, children of stardust, spun from the collapse of a cloud billions of years ago. The birth of the solar system is not just the beginning of Earth's history, it is the beginning of our own. Close your eyes again and let the memory of the newborn solar system fade behind you. Imagine drifting closer to the world that will one day be your home. But it is not blue and green. It is not covered in oceans or forests. The Earth we now approach is wild, young, and dangerous. A glowing sphere of fire and stone, wrapped in haze. This was Earth, around 4.5 billion years ago. A planet so young, it still bore the marks of its violent creation. Imagine a ball of molten rock, its surface shifting, breaking, and reforming with every passing moment. Volcanoes towered higher than mountains today, erupting endlessly, pouring rivers of lava across the ground. The heat was unbearable, not just from the sun above, but from within the earth itself. Radioactive elements in its core were decaying, releasing energy. Countless collisions with leftover planetesimals, rocky fragments still roaming the early solar system, added even more heat, each one an explosion powerful enough to vaporize entire regions. The young planet glowed, its crust unstable, constantly torn apart by impacts and eruptions. If you could stand on its surface, though you could not survive, you would see skies filled with smoke and dust, asteroids the size of cities streaked through the atmosphere, slamming into the molten ground. The air would be thick with steam, carbon dioxide, and poisonous gases. There were no oceans yet, no breathable air, no life. And yet, this was the foundation stage, the raw canvas on which everything else would be painted. Beneath the fiery surface, heavier elements like iron and nickel sank downward, pulled by gravity. They formed Earth's metallic core, deep and hidden, still churning hot today. Above that, lighter silicates floated upward, creating the mantle. And above the mantle, the first fragile crust began to take shape. This process, called planetary differentiation, gave Earth its structure, a core, a mantle, and a crust. Though it seemed chaotic, it was the beginning of order. The moon, fresh from its birth after the giant collision with Theia, loomed close, much closer than it does today. It filled the sky like a giant lantern, tugging fiercely at Earth's molten tides. Its gravity slowed Earth's rapid spin little by little, each day lengthening from a chaotic 6 hours at first to longer cycles. The Earth-Moon dance began here, setting rhythms that would one day shape life itself. But life was still far away. Right now, the Earth was in survival mode. Its young atmosphere, thick with carbon dioxide and nitrogen, trapped heat and swirled with lightning storms. Imagine the skies flashing constantly, thunder echoing across oceans of lava. Volcanoes released gases like hydrogen sulfide and ammonia, filling the air with a bitter, choking scent. And yet, these same gases were ingredients that one day under calmer skies would play a role in the chemistry of life. Water was arriving, though not in the calm form of rivers and lakes. Icy comets from the outer solar system may have collided with Earth, bringing frozen water that vaporized into steam. Volcanoes too released water vapor as they erupted, filling the atmosphere with moisture. Over millions of years, as the surface slowly cooled, this steam condensed. It rained, not for hours or days, but for centuries, for millennia, until the first oceans filled the craters and lowlands of the planet. But in this stage, we are still in the heat. The rain has not yet fallen in earnest, the oceans not yet formed. For now, Earth remained a world of fire. Yet even in this violent infancy, patterns were being set. The constant bombardment, called the late heavy bombardment, ensured that Earth was no gentle cradle, but it was also delivering new materials, seeding the young world with carbon, nitrogen, and water, the building blocks of biology. Every meteor strike was both destruction and delivery. The surface, constantly reshaped, hinted at what would come. Plates of rock fractured and drifted across the magma ocean. This was the earliest whisper of what would evolve into plate tectonics, the restless movement of Earth's crust that builds mountains, opens oceans, and fuels volcanoes. Already, though invisible to us, the Earth was preparing for a dynamic, ever-changing future. The molten planet was noisy too, though not with sound as we know it. The ground quaked with every impact. Rivers of lava hissed and bubbled. The core roared with energy. And above, the sun was brighter now, stabilizing after its turbulent birth, sending flares of radiation outward. Its solar wind pushed against Earth's atmosphere. Without protection, Earth might have lost those gases forever. But the molten core of the Earth was doing something miraculous. It was generating a magnetic field. As molten iron in the core churned and swirled, it created a dynamo effect, producing invisible lines of magnetism that stretched into space. This magnetic field shielded Earth from much of the sun's harsh radiation, preserving the young atmosphere, guarding the fragile beginnings of habitability. From the very start, Earth was not just a planet of fire and stone, but a planet with defenses, a guardian of its own potential. Slowly, ever so slowly, the fury lessened. The impacts became smaller, less frequent. The lava cooled in places, forming darker, solid rock. Islands of crust floated on seas of molten mantle, sometimes sinking back down, sometimes surviving. These first patches of crust were temporary, but they were steps towards stability. The planet still looked nothing like the one you know. No blue skies, no continents, no green fields or forests, but it was alive with motion. Volcanoes birthing mountains, impacts carving basins, molten rock hardening into solid stone. Time stretched on, millions upon millions of years, and Earth grew more stable, more ready. To us, these fiery beginnings might seem unwelcoming, but to the cosmos, this was the natural order. Every rocky planet passes through this crucible. Every world must endure its molten childhood before it can cool, before it can host oceans and atmospheres, before it can dream of life. So imagine, as you rest, the earth glowing softly beneath a young sun, wrapped in haze, seas of fire lapping against newborn mountains, a planet in the making, forged in heat and chaos, already carrying within it the seeds of oceans, skies, and life yet to come. This is Earth as a molten planet, fierce, restless, and unrecognizable, but beautiful in its own way. For without this fiery youth, without this trial by magma, the story of our world could never have begun. Imagine the Earth again, still young, still glowing, still restless in its molten infancy. The crust is fragile, the skies are heavy with poisonous gases, and the surface is scarred from endless bombardments. It seems as though this world has already endured enough chaos, and yet the most dramatic event of its entire early history is still to come. It begins with a wanderer somewhere in the crowded lanes of the early solar system. Another planetary embryo drifts closer. Astronomers call it Theia, a body about the size of Mars. Like Earth, Theia was forged in the same swirling disk of dust and gas that birthed the sun and planets. For millions of years, it followed its orbit quietly, but its path was unstable. Slowly, gravity tugged it closer and closer to Earth. One day, though day is too simple a word for a time when the Earth spun much faster, their paths crossed. Theia collided with the young Earth in a cosmic event so violent, so unimaginable, that it changed our planet forever. The impact was not a glancing bump. It was a collision of worlds. Theia struck Earth at an angle, its speed tremendous, its energy beyond measure. The force of the impact melted vast portions of Earth's surface, vaporizing rock, scattering molten debris into space. Entire mountains were obliterated in an instant. The planet itself wobbled, reshaped by the blow, but the story did not end in destruction. Out of chaos came creation. Much of Theia merged with Earth, adding mass, thickening its mantle, enriching its composition. Other fragments were blasted outward, flung into orbit around Earth. At first, they formed a fiery ring of debris, glowing arcs of molten rock circling the battered planet. Over time, gravity drew these fragments together. They clumped, merged, and grew until a new companion took shape. The moon. The moon's birth was an extraordinary gift. It began its life far closer to Earth than it is today. In those early nights, had there been eyes to see, the moon would have filled the sky, vast and luminous, appearing perhaps 10 times larger than it does now. Its gravity pulled fiercely on Earth, stirring massive tides in oceans of molten rock. Over billions of years, the moon would slowly drift away to the distance where it rests now, but its presence would remain constant, shaping Earth's destiny in ways both subtle and profound. One of the moon's most important roles was stabilizing Earth's tilt. Without it, Earth might have tumbled unpredictably, its axis wobbling wildly, its climate swinging between extremes, too chaotic for life to endure. But the moon's steady gravitational tug held Earth in balance. This gave the planet long-term stability, with seasons that could nurture life when the time was right. The giant impact also gave Earth something else: energy. The collision reheated the planet, melting much of the crust and leaving behind a magma ocean. The young Earth glowed once more, its surface churning with molten stone. But hidden within this chaos was a new structure. Earth's metallic core had grown larger, richer in iron and nickel, strengthening the magnetic field that already shielded the planet from solar winds. This invisible field, born deep within the Earth, would prove essential for preserving the atmosphere and protecting life in the distant future. The moon itself was also transformed. Unlike Earth, It was too small to hold onto an atmosphere for long, and too small to keep liquid water. Its surface cooled quickly, preserving the scars of its violent birth. Every crater we see today is a memory of those early times, frozen in place, untouched by weather or oceans. The moon became a kind of museum, a permanent record of the solar system's chaotic youth. Imagine, for a moment, standing on the surface of that early Earth. Though in truth you could not survive it, the sky would be glowing with fire, debris still raining down, lava rivers flowing in every direction. Above, the moon would loom impossibly large, a glowing orange orb still half formed, its surface molten and bright. The tides, driven by its closeness, would rise and fall with unimaginable force, pulling entire seas of magma across the surface. It was violent, it was strange, but it was also magnificent, a dance between two newborn worlds. This cosmic partnership, forged in collision, would define Earth's path. The moon gave Earth balance, the moon gave Earth tides, the moon gave Earth a steady rhythm of days and nights that would one day guide the cycles of living things. And all of it began with that singular, violent impact when two worlds collided and became one. Over millions of years, the chaos subsided. The ring of debris settled fully into the moon. The earth cooled again, though slowly, painfully, over eons. Volcanic eruptions released gases, thickening the atmosphere. Water vapor rose, condensed, and rained down in endless storms, beginning to fill the first oceans. The earth, reshaped by fire, began to prepare itself for the next chapter. The giant impact was not just an accident, it was part of the cosmic process, the natural way planets evolve. Other worlds may have had similar collisions. Some lost their moons, others gained multiple. But Earth's story was unique, and its outcome gave us a planet with just the right balance of tilt, spin, and protection to make life possible. Tonight, as you drift toward sleep, think of the moon shining above you. It is not just a cold rock in the sky. It is a relic of that ancient collision, a reminder that our planet was forged not only in fire, but also in partnership. Without the moon, Earth would be a very different place, perhaps too unstable for forests, too wild for oceans, too chaotic for you and me to ever have existed. The moon is our twin, our companion, born from a single act of cosmic violence. And even now, billions of years later, it drifts a little farther away each year, inch by inch, a reminder that creation is never finished, and that the story of Earth is always in motion. The Earth after the giant impact was a world remade, a globe of fire, a seething ocean of magma, and above it all, the newborn moon, glowing and close. Yet, even in such chaos, time was at work, patiently shaping the world we know today. Slowly, steadily, Earth began to cool. Cooling was no simple process. The energy released by the collision with Theia had left the planet molten nearly through and through. Vast seas of magma stretched across its surface, their waves rising and falling under the pull of the nearby moon. Every impact from leftover asteroids reheated the surface. Every eruption of a volcano released more fire, but heat also escaped into the dark of space. The Earth radiated energy away like an ember, slowly losing its furious glow. As the molten ocean cooled, the first skin of solid rock began to form. It was thin, fragile, and temporary, but it was the beginning of a crust. Imagine the surface of a pudding, forming a skin while still hot and liquid beneath. The Earth's first crust was like that, floating on molten mantle, cracking easily, and sinking back when broken. This early crust was basaltic, dark, and dense, made of the silicate minerals that floated upward when heavy metals sank to the core. It did not yet resemble the continents of today. It was patchy, unstable, forever reshaped by impacts and eruptions, and yet it was a foundation. The Earth's interior also continued to sort itself. Heavy iron and nickel sank toward the center, forming a dense metallic core. Around it, lighter silicate rock made up the mantle. This process of differentiation gave Earth its layered structure: core, mantle, crust. Deep inside, the outer core remained molten, swirling and churning, creating a magnetic field that reached far into space. This invisible shield kept the young atmosphere from being stripped away by solar winds. Even then, Earth was protecting its own potential. Above the crust, the skies were filled with steam and gas. Volcanic eruptions poured water vapor, carbon dioxide, and nitrogen into the air. The atmosphere was thick and heavy, nothing like the air you breathe now. It was toxic, a shroud of carbon dioxide and ammonia, but it trapped heat, keeping the young Earth from freezing beneath a faint, young sun. And then came the rain. For millions of years, the planet's skies released storms beyond imagination. Clouds of steam condensed, and water fell, not for days or weeks, but for centuries. For millennia, the surface hissed and bubbled as raindrops met hot rock. Rivers formed, pooling in low places, collecting in basins. Oceans grew, filling the scars of impacts, spreading across the world. Slowly, Earth was transformed from a world of fire to a world of water and stone. With oceans came change. The crust, now cooled in places, began to break into plates. These plates floated on the softer mantle beneath, moving slowly, colliding and pulling apart. It was the birth of plate tectonics. Though in its earliest, most primitive form, volcanoes rose where plates cracked, mountains were pushed up where they collided. Even in this young age, the planet was restless, always reshaping itself. The moon above kept pulling on the oceans, creating tides that surged far higher than today. Water washed across the land, back and forth, grinding stone into sand, carrying minerals into the sea. This endless motion mixed the planet's chemistry, preparing ingredients for the life that was still far in the future. The first continents began as small islands, patches of lighter rock that floated higher than the denser basalt. Over time, these proto-continents grew as volcanic eruptions added new layers. They drifted slowly, carried on the moving plates, merging and breaking apart again. Though they looked nothing like the continents you know, their beginnings lay here in those early days of cooling. Imagine, if you will, standing at the edge of one of these newborn islands. Though no eyes yet existed to see it, the sky above would be filled with heavy clouds, the air thick with carbon dioxide. Lightning flashed often, storms rolled endlessly, rain poured down, and the land steamed under its touch. The sea was dark, filled with minerals leached from the land, its waves tugged violently by the looming moon. It was a raw, alien world, but already it had oceans. Already it had land. Already it had cycles of rain and tide. These were the rhythms upon which life would one day depend. The cooling of Earth, the formation of crust, the falling of endless rain, all of it was preparation, laying the groundwork for the miracle to come. Time passed, measured not in years, but in millions of years. The crust grew thicker, the oceans deeper, the atmosphere heavier. Impacts from asteroids grew less frequent, though still occasional, carving craters and adding new material. The Earth's surface, though still violent, grew more stable. The planet was settling into its role as a habitable world. It is humbling to think that every mountain, every valley, every forest you see today can trace its lineage back to these first fragments of crust. The continents that cradle cities and nations began as small, fragile islands floating on molten seas. The oceans that cover most of the planet began as raindrops falling on hot stone. Out of fire and storm, Earth became a planet of land and water. As you drift toward sleep, hold this image in your mind. A young world, its fury slowly softening, its fires slowly cooling, its surface slowly hardening into rock. Rain falls endlessly, filling oceans, shaping coastlines. The moon pulls at the seas, guiding their rhythms. Volcanoes breathe steam into the sky, feeding storms that never end. It is not yet the Earth you know, but it is on its way. The cooling of Earth and the formation of crust was not just a stage in history, it was the foundation of everything that followed. Continents, oceans, atmosphere, life. The fiery planet became a stony planet, and the stony planet became a watery planet. Out of this balance of rock and water, the story of life would soon begin. Close your eyes and picture the earth as it was after the great rains had begun to fall, after the molten seas had hardened into dark rock, after the moon had steadied the planet's wobble. There is ocean, there is crust, there are storms, but above all this is a sky, not the blue sky you know, but a heavy shroud, an atmosphere entirely alien to human lungs. The Earth's first atmosphere was born in fire, long before the rains fell, long before oceans pooled in lowlands. Volcanoes covered the world. Their eruptions poured gases into the air: carbon dioxide, nitrogen, methane, ammonia, hydrogen sulfide, and thick water vapor. With every eruption, with every plume of steam and ash, the atmosphere grew. It was not the first atmosphere Earth ever held. In truth, there had been an even earlier one, a thin cloak of hydrogen and helium, left over from the birth of the solar system. But that atmosphere was fragile. The young sun, still wild and unstable, blasted the planet with fierce solar winds. Without a strong gravity to hold them, those light gases were stripped away into space. What remained was nothing. Earth was bare. So it was the volcanoes that built the second, stronger atmosphere, what we call the primordial atmosphere. Imagine, if you can, skies thick with steam, clouds as dense as smoke, lightning splitting the heavens again and again. Rain fell, but it evaporated as soon as it touched the burning ground, rising back to the sky in endless cycles. The air was poisonous to you and me. Breathe it in, and it would scorch your lungs. There was no oxygen, not yet. Instead, carbon dioxide dominated, mixed with methane and ammonia. The world smelled of sulfur, of fire, of minerals torn from the planet's depths. It was not a place for humans, but it was exactly the kind of place where chemistry could begin to dance, because in that thick, stormy sky, something extraordinary was happening. Lightning, striking through clouds heavy with methane, ammonia, and water vapor, provided energy to break bonds, to rearrange molecules, to forge new compounds. In the oceans below, these compounds fell as rain, mixing with minerals from the land, forming what scientists sometimes call a primordial soup. Though life was still far away, its ingredients were beginning to collect. The sun, too, played its part, though weaker then than it is today. It still bathed Earth in ultraviolet radiation. These rays broke apart molecules in the upper atmosphere, creating reactive fragments that joined with others, making new and more complex compounds. Every day, the atmosphere was a chemical workshop, powered by light, lightning, and heat. At the same time, the atmosphere served another role. It blanketed the Earth, holding in heat. Without it, the young planet might have frozen, for the sun shone only faintly in those days, no more than 70% as bright as it does now. This is called the faint young sun paradox. How could Earth stay warm under a weak sun? The answer lies in those thick greenhouse gases, carbon dioxide and methane trapping warmth, keeping the oceans from freezing solid. So the first atmosphere was not only hostile, it was protective. It was the shield that kept Earth warm enough for oceans to remain liquid, for chemistry to continue, for life to one day find a home. But this atmosphere was also unstable. Volcanic eruptions could change its composition quickly, belching ash and gases that darkened the skies. Impacts from asteroids could strip portions away or add new chemicals. The atmosphere of early Earth was a restless, ever-changing veil, reflecting the turbulence of a young planet. Imagine the scene. You stand at the edge of a steaming ocean. The air is thick, heavy, and red with dust and gases. The sun glows dimly through the haze, a pale disk in a sky of browns and oranges. Thunder growls, lightning cracks, rain falls in heavy sheets, only to hiss and vanish into the warmth of the ground. Volcanoes rise in the distance, their plumes feeding the sky, their lava feeding the land. It is not a world you could walk through, but it is a world alive with energy, restless, fertile, and waiting. Over time, as rain fell endlessly, carbon dioxide dissolved into the oceans, combining with minerals to form carbonates. Slowly, the air thinned of this heavy gas. Nitrogen grew dominant, a background element that would remain through Earth's history. But without oxygen, it was still a suffocating sky. The seas remained dark, filled with iron, unoxidized, greenish-black in color. This stage of Earth's history lasted for more than 1 billion years. For 1 billion years, the planet breathed carbon dioxide and methane, storm and sulfur. For 1 billion years, the skies were heavy and strange. But during that time, deep in the oceans, life was beginning. Tiny microbes, born of the chemical dances sparked in this thick atmosphere, would soon rise. They would eat, they would multiply, and they would change everything. One day, billions of years later, their descendants would release oxygen into the air. They would make the skies blue, they would make the seas clear, and they would make the world breathable. But that is for another night. For now, the Earth is wrapped in its first true atmosphere, thick, toxic, stormy, but full of possibility. As you drift toward sleep, imagine those ancient skies, heavy and glowing, alive with lightning. Imagine the endless rains falling into the oceans, carrying with them the ingredients of life. The air may not yet have been for us, but it was a cradle, holding the warmth, shielding the seas, and preparing the stage for the miracle to come. Picture the earth, wrapped in clouds of steam and gas. The ground hisses and steams, volcanoes roar, and the young atmosphere is thick with carbon dioxide and nitrogen. And then, slowly at first, and then endlessly, water begins to fall, not in passing showers, not in summer storms, but in torrents that last for centuries, for thousands of years, for millions. Rain poured down from skies heavy with vapor, fed by volcanoes and by icy gifts from space. Drop by drop, storm by storm, the surface filled. Craters became lakes, valleys became rivers, entire basins became seas, and the seas joined together, spreading across the globe until Earth was transformed into an ocean world. But water's journey to Earth did not begin here. Its story began long before, in the birth of the solar system itself. Some of Earth's water came from deep within the planet, released as steam by volcanoes as the molten mantle cooled. Trapped inside the rocks of Earth's interior, water had been carried from the ancient nebula that birthed the sun. When the planet first formed, that water was locked away, waiting for the day it would rise into the sky and fall back as rain. But there was another source, far beyond Earth, in the cold outer regions of the solar system. Icy comets and water-rich asteroids drifted, leftovers of planet formation. They carried frozen water, carbon compounds, and minerals. For hundreds of millions of years, these icy wanderers rained down upon Earth, each impact adding more water to the planet's surface. The late heavy bombardment, a storm of asteroids and comets striking Earth between 4.1 and 3.8 billion years ago, delivered vast amounts of this cosmic ice. It was violent, yes. Impacts shook the surface, melted rock, carved craters, but in their destruction, they gave Earth its oceans. Imagine the scale of this transformation. From a dry, rocky sphere wrapped in poisonous air, Earth became a world of rivers, lakes, and seas. By around 4 billion years ago, great oceans stretched across the surface, covering most of the planet. The Earth that had glowed red and molten was now blue and glistening, a water planet unlike almost any other in the solar system. The presence of water changed everything. It cooled the surface more quickly, carrying heat into the atmosphere and into space. It weathered rocks, breaking down minerals, carrying them into the seas. In the oceans, chemistry stirred. Salts dissolved, iron washed in, carbon dioxide bubbled out. Slowly, the seas grew rich in nutrients, creating a chemical soup. And within this soup, life was preparing to take its first steps. But long before life, water itself shaped the earth. Tides surged under the pull of the moon, far stronger than they are today. Imagine waves not meters high, but kilometers, sweeping across coasts, grinding stone into sand, carrying minerals far and wide. These tides mixed the oceans, spreading nutrients evenly, stirring the cauldron of chemistry. Rivers carved channels into the young crust, sediments collected in basins, the constant cycling of water. Rain to river, river to sea, sea to cloud, cloud to rain, began its endless loop. This cycle, begun billions of years ago, continues still, unchanged in its essence. Every raindrop that touches your skin today is part of that ancient dance, part of a cycle older than life itself. The oceans also helped regulate the planet's climate. Water absorbs heat, holding it, spreading it slowly. It prevented Earth from freezing during the dim days of the young sun, and it kept the planet from overheating during violent eruptions. In this way, the oceans became Earth's great moderator, balancing extremes, making the world more stable. And there is something else to consider. When we look at other planets, Venus, dry and scorching, Mars, frozen and barren, we realize how rare Earth's gift truly was. Venus may once have had water, but it boiled away under a runaway greenhouse effect. Mars, too, shows signs of ancient rivers and seas, but its thin atmosphere let them escape into space. Only Earth held on to its oceans. Only Earth found the balance to remain blue. Think of the beauty of it. A planet wrapped in oceans, shimmering under a dim sun. Clouds drifted above. Storms swirled across the seas, and the moon pulled the tides back and forth. For the first time, Earth looked almost like the world you know today. Not yet green, not yet alive in the way we imagine, but alive in motion, alive in water. The arrival of water was more than just a physical change. It was the opening of possibility. In the depths of those oceans, warmed by volcanic vents and stirred by tides, molecules collided, formed, broke, and formed again. Life was still billions of years away, but the stage was set. Without water, there could be no cells, no DNA, no plants, no animals, no humans. Water is not just part of Earth's story, it is the essence of Earth's story. So as you drift into rest, imagine those endless rains, those roaring tides, those first vast oceans spreading across the globe. Picture the Earth shining in space, blue for the first time, its seas glistening under a young sun. This was the moment when Earth became not just a planet, but a world of water, a world of promise, a world ready to begin the long journey toward life. The oceans of early Earth were dark, mineral-rich, and restless. Their waves crashed under a red-orange sky filled with storm clouds. Lightning flashed, volcanoes erupted, and the moon pulled the tides with a strength far greater than today. It was a world in motion, a world of endless chemistry, and somewhere in this restless sea, the first spark of life appeared. Life did not begin in an instant. There was no single flash, no single moment that we can point to with certainty. Instead, life arose slowly, in steps that spanned millions of years. What we call the spark was a process, a gradual weaving together of molecules into something more than mere chemistry. The building blocks of life were already present. Water filled the oceans. Carbon, hydrogen, oxygen, and nitrogen were abundant in the air and sea. Minerals washed into the oceans from the land. Lightning struck again and again, providing energy. Ultraviolet rays from the young sun bathed the planet, and at the bottom of the oceans, volcanic vents released heat, gases, and minerals into the surrounding waters. Earth was a laboratory, vast and restless, where molecules collided endlessly. In this laboratory, simple compounds formed: amino acids, the building blocks of proteins; nucleotides, the seeds of DNA and RNA; fatty acids, capable of forming membranes. These molecules did not remain isolated. They gathered in pools, in tide pools warmed by the sun, in droplets along the shores, in deep-sea vents rich in minerals. There they reacted, joined together, broke apart, and reformed in countless variations. Imagine lightning striking a shallow pool, splitting water molecules, rearranging carbon compounds. Imagine droplets forming along a coastline, their edges coated with fatty acids that self-assembled into fragile bubbles. Inside these bubbles, other molecules gathered, protected, concentrated. Chemistry began to take shape, to organize itself. These were the first steps toward life. One of the great mysteries is where exactly this spark took place. Some scientists believe life began in shallow pools, where cycles of wetting and drying concentrated molecules, encouraging them to link into chains. Others believe it began in the deep ocean, near hydrothermal vents. At these vents, hot water, rich in minerals, gushed into the cold sea, creating a gradient of energy. Within this gradient, molecules could form, grow, and combine in ways impossible elsewhere. Perhaps life's first breath was taken in the darkness, deep beneath the waves. Wherever it began, one crucial step was the formation of self-replicating molecules. RNA, a cousin of DNA, may have been the first. Unlike DNA, which requires complex machinery to copy itself, RNA can act as both information carrier and catalyst. It can store instructions and also help reactions take place. Imagine a molecule that not only exists, but can also make a copy of itself. That was the beginning of evolution. Once replication began, natural selection followed. Some molecules were more stable than others. Some copied themselves more quickly or more accurately. These molecules survived and spread. Chemistry was no longer random. It had direction. Slowly, over millions of years, molecules became more complex, more efficient, more alive. At the same time, fatty acids formed membranes, tiny bubbles that trapped molecules inside. These bubbles, called protocells, created a protected space where chemistry could concentrate. Inside them, RNA and proteins could interact, shielded from the chaos of the outside world. For the first time, the ingredients of life were contained, organized, and able to grow. It is humbling to think of this stage. No plants, no animals, not even bacteria yet. Only tiny droplets, invisible to the naked eye, drifting in the sea. And yet, within them, life's future was unfolding. Every creature, every tree, every human can trace its story back to these fragile protocells, floating in a dark, mineral-rich ocean 4 billion years ago. But life is not defined only by chemistry. Life requires energy. For the first cells, energy may have come from chemical gradients at hydrothermal vents. There, molecules flowed across the walls of mineral chimneys, carrying energy in their movement. Protocells may have harnessed this energy, using it to drive reactions, to grow, to divide. In this way, the first metabolism began. Slowly, protocells became more stable. Their membranes grew stronger. Their RNA became more efficient. Proteins, chains of amino acids, began to help with tasks, speeding up reactions, protecting delicate molecules. Cooperation was born. Life was no longer a single molecule, but a community of molecules working together inside a fragile bubble. And then, one day, the first true cells appeared. They were simple, yes, but they could grow, divide, and make copies of themselves. They could use energy, respond to their environment, and pass information to their offspring. With these cells, life had crossed the threshold. The earth was no longer a lifeless world of rock and water. It was alive, We call these earliest cells prokaryotes, ancestors of bacteria. They had no nucleus, no complex structures, only a membrane and the machinery to survive. Yet from their simplicity, all future life would unfold. For nearly 2 billion years, these microbes would rule the planet, shaping its oceans, shaping its air, shaping its future. Imagine them, too small to see, drifting through ancient seas. They lived in darkness, feeding on minerals, splitting and multiplying. Their colonies grew on rocks, around vents, in shallow pools. They left behind faint chemical traces, fossils not of bones, but of isotopes, the quiet fingerprints of their presence. They were Earth's first living things, and they would be its only living things for an unimaginable stretch of time. As you lie back now, imagine this quiet revolution. No fanfare, no great beasts, no forests or mountains, yet alive with animals, only molecules, bubbles, and tiny cells hidden in the vast oceans of an ancient world. But within those cells, the story of life had begun. The spark had caught. The journey from chemistry to biology was complete. Without sound, without spectacle, Earth had become more than stone, more than water, more than air. Earth had become alive. The Earth was no longer merely a planet of rock and water. It was alive, though invisible to the eye. Within the vast oceans, trillions upon trillions of tiny cells floated, divided, and multiplied. These were the first microbes, the earliest inhabitants of our world, simple yet astonishing in their power. Though microscopic, they held the seeds of everything that would come after. Life at this stage was fragile. Each microbe, no bigger than a speck of dust, relied on the chemistry of the oceans to survive. They absorbed nutrients from the water around them. They split, dividing endlessly, creating generations of cells. They were tiny engines of life, quietly transforming the planet in ways that no one could yet see. Many of these microbes were anaerobic, meaning they could survive without oxygen. In fact, there was almost no oxygen in the atmosphere yet. The air was still thick with carbon dioxide, methane, and nitrogen. These organisms drew energy from chemicals in the water and the minerals of the seafloor. Some absorbed hydrogen, some used sulfur, and some fed on the molecules released from volcanic vents. Each one was a tiny miracle, adapted perfectly to the harsh, alien conditions of early Earth. Colonies began to form in shallow pools. Microbes gathered in sticky layers, creating mats of cells that clung to rocks or floated on the water's surface. In the darkness, near hydrothermal vents, other communities clustered around mineral-rich chimneys, where heat and chemicals provided energy. These early colonies were the first ecosystems, tiny worlds within a world. Over millions of years, microbes began to evolve. Mutations occurred in their genetic material, creating new variations. Some could use sunlight for energy, performing photosynthesis in its simplest form. These were the ancestors of cyanobacteria, the first organisms capable of converting sunlight, water, and carbon dioxide into chemical energy, a process that would eventually fill the atmosphere with oxygen. This oxygen production was subtle at first. Tiny amounts of oxygen diffused into the oceans, reacting with iron and other minerals. Vast, rust-colored deposits formed on the ocean floor, known today as banded iron formations. These were the fingerprints of life, etched in stone, evidence that microbes were already changing the chemistry of the planet. The oxygen would take millions of years to accumulate in the atmosphere, but even then, life was quietly reshaping Earth. Microbes were also laying the foundations for cooperation. Some formed symbiotic relationships, living in clusters where each microbe provided something the others needed. Life was beginning to organize itself, not just as individual cells, but as communities. From these simple interactions, the complexity of ecosystems would one day emerge. The energy that microbes used came in many forms. Some absorbed chemicals from the seafloor, some used sunlight, some broke down organic molecules that had accumulated in the oceans. Each strategy was a tiny experiment in survival, a way to thrive in a world without oxygen, without plants, without animals. These organisms dominated the planet for billions of years. They covered rocks, floated in seas, formed slimy layers on the ocean floor. They were Earth's first gardeners, slowly altering the chemistry of the oceans and the atmosphere. Without them, the oxygen-rich air that we breathe today would never exist. Without them, the future of complex life would never unfold. Imagine drifting silently through these early oceans. The water is dark, but teeming with life, invisible to the eye. Clouds of microbes swirl with the currents. Tiny flashes of chemical reactions light up in the depths. Hydrothermal vents hiss, releasing warmth and minerals, providing energy for these first communities. It is a world quiet to human senses, but full of invisible activity, a silent revolution that will one day make the planet green, blue, and alive. Even the simplest microbes were innovators. Some began producing sticky substances that allowed them to adhere to surfaces, forming protective layers. Others evolved primitive ways to move through the water, following gradients of nutrients. Evolution was at work, quietly experimenting, selecting, and refining. Over billions of years, these small changes would accumulate into the vast diversity of life that covers the earth today. The first microbes remind us that life's power is subtle. They were tiny, unseen, and seemingly insignificant, yet they changed the world profoundly. They oxygenated the oceans. They stabilized the climate. They created ecosystems. They set the stage for multicellular life, for plants, for animals, for humans. All of it began here, in the dark, mineral-rich seas, with creatures no bigger than a drop of water. As you drift into sleep, picture these ancient oceans, calm and restless at once. Imagine billions of tiny cells, invisible, yet alive and thriving, drifting with the currents, feeding, multiplying, transforming the waters of Earth. They are the quiet ancestors of all life, the first whisper of biology on a once lifeless planet. The first microbes teach us patience and persistence. Life began small, unnoticed, and fragile. Yet from these humble beginnings, everything we see today would one day arise. The earth itself, oceans, continents, forests, and cities all owe their existence to these earliest inhabitants. Imagine the earth more than 2 billion years ago. The oceans are alive with microbes, teeming in invisible numbers. The sun casts a pale light through skies, still heavy with carbon dioxide and nitrogen. Volcanoes continue to release gases, and tides, pulled by the moon, churn the seas in a slow, steady rhythm. In this world, something extraordinary is quietly taking shape. Oxygen, the gas that would one day fill the skies and allow life as we know it. The pioneers of this transformation were cyanobacteria, microbes capable of photosynthesis. Unlike earlier microbes, which gained energy from chemicals in the water, these organisms could use sunlight. They absorbed carbon dioxide and water, and with energy from the sun, they produced sugar and, as a byproduct, oxygen. For the first time, the Earth's biosphere began producing a gas that was toxic to most existing life, yet essential for the future. At first, the oxygen didn't linger in the atmosphere. It reacted with minerals dissolved in the oceans, particularly iron. This reaction created rust, forming layers of banded iron deposits on the seafloor. These formations are still visible today, silent monuments to the first oxygenation events. Laid down over millions of years, the oxygen was trapped in the oceans, and life continued largely unchanged on the surface. Slowly, the balance began to shift. The oceans could no longer absorb all the oxygen produced. Minute amounts began to escape into the atmosphere. For the first time, Earth's air contained free oxygen, though in tiny concentrations. This was the beginning of a transformation so profound it would alter the planet forever. This period, known as the Great Oxidation Event, began around 2.4 billion years ago. For hundreds of millions of years, oxygen levels rose gradually, fluctuating as microbial life, volcanic activity, and chemical reactions in the oceans interacted. The sky remained mostly hazy, tinged with methane and carbon dioxide. But a new force was building invisibly: oxygen. The rise of oxygen had consequences. For many anaerobic microbes, oxygen was poisonous. Populations of these organisms declined, replaced by species that could tolerate or even use oxygen. Life began to diversify in response to this new chemical environment. Microbial evolution accelerated. Slowly, the blueprint for more complex life was emerging. Oxygen also transformed the Earth itself. With increasing amounts in the atmosphere, chemical reactions on land and in the oceans changed. Rocks weathered differently. The composition of the seas shifted, and the climate began to stabilize. Oxygen allowed the formation of the ozone layer, which would one day protect life from harmful ultraviolet radiation. The stage for terrestrial life, for plants, for animals, for us, was being set. Imagine drifting over the early oceans. The water glows faintly in places, stirred by currents, and filled with thriving cyanobacteria. Tiny bubbles rise to the surface, carrying oxygen into the air. The ocean floor is marked with layers of iron deposits, evidence of a long chemical battle between the elements and the products of life. Above, the sky remains heavy and murky, yet it now contains a new element: oxygen, a harbinger of future life forms. Oxygen's arrival was both a blessing and a challenge. It allowed future life to evolve, to use aerobic respiration and extract more energy from food than anaerobic metabolism ever could. Yet, for existing life, it was a crisis, forcing adaptation, innovation, and sometimes extinction. Life was being rewritten by chemistry, a reminder that evolution is not gentle, but relentless. Over millions of years, oxygen continued to accumulate. Clouds, seas, and soils absorbed some, but slowly, atmospheric levels rose. The sky began to clear, the haze thinning. Sunlight could penetrate more deeply, warming the oceans and land. This oxygen-rich environment enabled the eventual rise of eukaryotes, cells more complex than the prokaryotic microbes that had dominated for billions of years. Inside these eukaryotic cells, organelles like mitochondria harnessed oxygen to generate energy, paving the way for multicellular life. And so, the Earth began to transform again. No longer was it only a planet of water and rock, of tides and storms. It was now a world with a breathable atmosphere, with the invisible presence of oxygen changing chemistry, biology, and climate. The work of tiny cyanobacteria, invisible to the naked eye, had begun to sculpt the planet on a planetary scale. As you drift toward sleep, imagine these ancient seas. Cyanobacteria float in sunlight, producing bubbles that rise endlessly. The ocean glistens faintly, currents swirl, and the distant moon tugs at tides. Above, the sky begins to hint at clarity, colored by the first free oxygen. Life's invisible hand is shaping the planet, silently and steadily, one molecule at a time. Oxygen's rise was a quiet revolution, subtle yet unstoppable. It prepared Earth for forests, for animals, for humans. It transformed a microbial world into one capable of sustaining complex ecosystems. And in those early bubbles and bands of iron, the story of our own existence was already being written. The Earth had been a world of single-celled microbes for over 1 billion years. Oceans teemed with prokaryotes, simple cells without a nucleus, surviving in every niche, from sunlit shallows to deep hydrothermal vents. Life was thriving, yet constrained, limited in complexity. And then, something extraordinary happened. The emergence of eukaryotes, cells with a nucleus, organelles, and the ability to do more than their ancestors ever could. Imagine the ocean billions of years ago. Currents swirl lazily over vast stretches of early continents. Tides rise and fall under the pull of the moon, and sunlight filters through waters now richer in oxygen. In this world, a remarkable partnership formed within a single cell. One cell engulfed another, but instead of digesting it, it kept it alive. This internal resident, a smaller cell, became an organelle, a mitochondrion. It generated energy, powering the host cell. This symbiotic union gave rise to the first eukaryotes. Eukaryotic cells were larger than prokaryotes. They could compartmentalize functions, storing DNA in a nucleus, producing proteins in ribosomes, and harnessing energy in mitochondria. These internal structures allowed for more sophisticated metabolism, faster growth, and eventually the ability to specialize. In essence, eukaryotes were cells with internal architecture, capable of more complex behaviors than simple microbes. This leap was not sudden. It was the result of billions of years of evolution and chemical experimentation. The presence of oxygen made it possible. Aerobic respiration, which uses oxygen to release energy from food, is far more efficient than anaerobic processes. With mitochondria harnessing oxygen, eukaryotic cells could sustain larger sizes, support more DNA, and develop new ways to interact with their environment. Energy, once a limiting factor, was now abundant. Eukaryotes began to diversify. Some remained single-celled, drifting in oceans, feeding on nutrients, or absorbing energy from light through early forms of photosynthesis. Others developed complex relationships with their surroundings, forming colonies that hinted at the future of multicellularity. These colonies allowed cells to cooperate, to specialize, to divide tasks Some cells became structural, others reproductive, creating the first simple tissue-like organizations. Imagine floating in those early oceans, invisible to the naked eye. Countless eukaryotic cells drift in the currents, glowing faintly with the reactions inside their mitochondria. Some gather in colonies, forming thin layers across rocks or the surface of shallow pools. They interact, they exchange materials, they adapt. Life is growing more sophisticated, more dynamic, more capable of shaping its environment. The emergence of eukaryotes also set the stage for evolution to accelerate. Genetic material could now recombine in new ways. Sexual reproduction, appearing later, would allow for an incredible variety of offspring, mixing traits and testing adaptations on a massive scale. Evolution, once slow and constrained, was now able to explore new possibilities more rapidly. Eukaryotes also began to interact with oxygen in new ways. Some incorporated it directly into metabolic pathways. Others adapted to survive fluctuations in oxygen levels. Life, once limited to simple anaerobic processes, was now expanding into a world where chemistry, energy, and structure could combine in increasingly sophisticated ways. These early eukaryotes were the ancestors of everything complex that would follow: algae, fungi, plants, animals, and eventually humans. They were invisible architects of Earth's future, quietly experimenting with internal structures, energy efficiency, and cooperative behavior. The oceans of this time were teeming not just with life, but with innovation. Eukaryotic cells could engulf prey, harness light, process nutrients more efficiently, and even move in response to their environment. They were more than cells. They were dynamic systems, capable of shaping the world they inhabited. As you drift toward sleep, picture this invisible revolution. The ocean glows faintly, currents swirl, and countless eukaryotic cells float, divide, and interact. Life is no longer simple. It has architecture, energy, and potential. Every cell carries within it the blueprint for everything that will follow. The Earth, once a planet of single-celled microbes, is now a world of cells capable of complexity, cooperation, and innovation. This step, the emergence of eukaryotes, was one of the most significant leaps in life's history. It set the stage for multicellularity, for diversity, and for the intricate web of life that eventually would cover the planet. The ocean was alive in ways more profound than ever before, and the story of life had taken its next dramatic turn. For over 1 billion years, eukaryotes drifted in Earth's oceans, thriving as single-celled organisms. Each cell lived independently, absorbing nutrients, dividing, and reproducing. But evolution, subtle and patient, was experimenting with a new idea: cooperation. Some cells began to stick together after division, forming small clusters. Others specialized, performing different tasks within these clusters. Slowly, the first multicellular organisms took shape. These early multicellular life forms were simple, almost invisible. Some were colonies of algae, floating in shallow seas, capturing sunlight for energy. Others formed filamentous structures, clinging to rocks or drifting with currents. These organisms were small, fragile, and easily disturbed by the tides or storms. Yet their innovation was profound. By joining together, cells could share resources, protect each other, and explore environments no single cell could conquer. alone. Imagine an ancient ocean teeming with single-celled eukaryotes. Among them, tiny clusters begin to form. Some cells specialize. One group gathers nutrients, another protects the colony, another reproduces. Though microscopic, these cooperative systems are the first hints of body plans, the earliest blueprints for complex life. The advantages of multicellularity were many. Clusters of cells could grow larger, accessing new light and nutrients. Specialized cells allowed more efficient metabolism and energy use. Colonies could survive environmental stress better than single cells, enduring waves, temperature fluctuations, and chemical changes. Life was becoming more resilient. Fossils from this time, around 1.2 to 1 billion years ago, reveal some of these early multicellular organisms. They were small, simple, and soft-bodied, nothing like the complex plants or animals of today. Yet they represented a turning point. Life was no longer confined to single cells. It was beginning to organize into structures, networks, and systems. Some multicellular organisms remained simple for millions of years, floating in oceans, feeding on sunlight, or absorbing nutrients from the water. Others developed more complex behaviors. Movement, even slight, became possible. Filaments could bend with currents. Colonies could orient themselves toward light, and some structures provided primitive protection from predators or environmental hazards. This era of life is often overlooked because the organisms were tiny, fragile, and lacked hard parts. There were no shells, no bones, no coral reefs yet, but these soft, flexible life forms set the stage for an explosion of diversity in later eons. Without multicellularity, the forests, the fish, the insects, and ultimately humans would never exist. Multicellular life also opened the door for genetic innovation. By coordinating multiple cells, organisms could experiment with new forms of growth, division of labor, and development. Natural selection could act not just on individual cells, but on the colony as a whole. Evolution had a new canvas on which to paint, far more intricate than before. Consider the oceans as a stage for this early drama. Currents sweep gently over vast seas, carrying clouds of cells and colonies. Tides, drawn by the moon, surge with gentle power, shaping coastlines and stirring nutrients. Storms pass, rain falls, and the sunlight filters through the waters, energizing photosynthetic organisms. Among this chaos and beauty, tiny multicellular life forms float, divide, and experiment with cooperation. By around 600 to 800 million years ago, multicellular life began to diversify more rapidly. Algae formed larger colonies, providing food and oxygen for other organisms. Soft-bodied animals like sponges appeared, simple structures capable of filtering water for nutrients. These early animals had no muscles, no nervous systems, yet they were pioneers, experimenting with shape, function, and interaction with the environment. Multicellularity was not just a physical development, it was a social experiment at the cellular level. Cells learned to work together, to communicate chemically, to divide roles. This coordination would later allow the evolution of tissues, organs, and eventually entire organisms capable of movement, sensation, and intelligence. As you drift toward sleep, picture these ancient oceans. Microscopic clusters float in currents, some forming colonies, some branching like tiny filaments. The water glistens, the sun penetrates faintly, and tides swirl gently under the moon's pull. Life, invisible yet abundant, is learning the power of unity, of cooperation, of complexity. From these humble beginnings, Earth would eventually host enormous forests, vast oceans filled with fish, swarms of insects, and the intricate ecosystems we know today. Every blade of grass, every bird, every human owes its existence to the quiet experimentation of these first multicellular life forms. The first multicellular life is a reminder that cooperation can transform the world from single cells to colonies, from colonies to organisms. Life was learning to organize, adapt, and thrive in new ways. And it was only the beginning of a journey that would reshape the planet forever. Imagine the oceans of Earth around 635 to 541 million years ago. The world is calm, yet dynamic, filled with multicellular life, learning to cooperate, to grow, to explore its watery environment. The oceans are deep, clear, and slightly enriched with oxygen, a gift from billions of years of cyanobacteria and microbial activity. And now, life begins to take shapes we can almost recognize. This period is called the Ediacaran, named after the Ediacara Hills in Australia, where fossils from this era were first discovered. These fossils reveal soft-bodied organisms, strange and alien by today's standards, yet they represent the first clear evidence of complex life on Earth. Unlike the invisible microbes or tiny colonies of earlier eras, Ediacaran life could be seen, albeit slowly, floating, crawling, or anchored in the oceans. Imagine drifting over a shallow Ediacaran sea. The seafloor is soft and sandy. Strange quilted forms rest on the sediment, resembling inflated pillows or fractal patterns, their soft bodies absorbing nutrients directly from the water. Others are discs, like circular mats or long fronds, waving gently in the currents. Some resemble tubes or ribbons, stretching across the sand, anchored at one end. They are silent, slow, and elegant, yet they signal a dramatic shift in the life's complexity. Ediacaran organisms were incredibly diverse in shape. Some were simple and flat, others more three-dimensional. Some could absorb food across their surfaces, others likely filtered water for nutrients. They had no hard skeletons, no shells, no teeth. Yet they were far larger than any life that had come before, some measuring over a meter across. These were the first organisms to occupy the space between the microscopic and the truly macroscopic. One remarkable aspect of the Ediacaran explosion is that it represents a period of experimentation. Life tried many forms, many body plans, many methods of interacting with the environment. Some lineages would die out, leaving no descendants. Others would give rise to the ancestors of animals we know today. The Ediacaran was, in a sense, a laboratory of evolution, a time when life explores the possibilities of multicellularity on a grand scale. The oceans themselves played a role in this explosion. Rising oxygen levels allowed organisms to grow larger and maintain more complex bodies. The seafloor was soft, allowing creatures to anchor themselves or move slowly across sediments. Currents and tides provided a steady flow of nutrients, and the chemistry of the oceans had stabilized enough to support ecosystems capable of sustaining larger organisms. Ediacaran organisms were pioneers in many ways. Some could move slightly, inching across the seafloor in search of nutrients. Others remained stationary, anchored in one spot, but interacting with the surrounding water. They introduced the first visible patterns of life: symmetry, segmentation, branching structures. These were early experiments in body plans, many of which would later be elaborated in the Cambrian Explosion. Imagine, if you can, a quiet Ediacaran sea. Sunlight filters through the water, illuminating strange, soft-bodied creatures. Quilted fronds sway gently, disc-shaped mats absorb nutrients from the currents. Tubes stretch vertically, anchored in soft sediments. Life is everywhere, yet silent, subtle, and graceful. It is a world very different from today, yet unmistakably alive. The Ediacaran period also set ecological foundations. Early predator-prey interactions were minimal, but the first simple relationships between organisms appeared. Some organisms may have scavenged detritus, others absorbed nutrients directly from the water. These interactions laid the groundwork for the complex food webs that would emerge later. By the end of the Ediacaran, life had become a diverse, visible presence in the oceans. Though many of these creatures would leave no direct descendants, they demonstrated that multicellular life could exist at a scale and complexity far beyond simple colonies. They prepared the stage for one of the most dramatic events in Earth's history, the Cambrian Explosion. As you drift into sleep, picture the Ediacaran seas, floating fronds, quilted discs, anchored tubes, strange and delicate forms that move and sway in silent currents. Life has grown visible, diverse, and experimental. Every organism, no matter how strange, is part of the story of complexity, cooperation, and innovation that will eventually lead to the rich tapestry of life on Earth today. The Ediacaran Explosion teaches us that evolution is patient, experimental, and often unpredictable. From invisible cells to soft, strange creatures on the seafloor, life is learning, adapting, and preparing for the future. And it is all unfolding quietly, invisibly, as the oceans carry these first macroscopic forms across the globe. Around 541 million years ago, Earth entered a remarkable period known as the Cambrian Explosion. For millions of years, life had been slow, subtle, and largely soft-bodied. But in the Cambrian, evolution accelerated, creating an incredible variety of organisms, many of which developed hard shells, exoskeletons, and structures that could fossilize. Suddenly, the oceans were filled with recognizable animals, swimming, crawling, and burrowing, shaping the world in ways never seen before. Imagine drifting through Cambrian seas. Currents flow gently, the sun filters through clear waters, and the seafloor is alive with movement. Strange creatures swim overhead, others scuttle along the sand, and some burrow into the sediment below. Sponges filter water for nutrients. Trilobites crawl across the ocean floor, and early arthropods explore every crevice. The oceans are no longer a quiet stage. They are a theater of life. The Cambrian explosion was driven by several factors. Rising oxygen levels allowed organisms to grow larger and develop active metabolisms. Multicellularity had matured, allowing for tissues, specialized cells, and complex body plans. Predation emerged for the first time in a significant way, creating evolutionary pressure for defenses like shells and spines. And the oceans were chemically stable, rich in nutrients and ready to support more complex ecosystems. One of the most iconic animals of this period is the trilobite. These segmented creatures crawled along the seafloor, protected by hard exoskeletons. Their eyes, some of the first complex visual organs in Earth's history, allowed them to detect predators and prey. Trilobites represent a new stage in evolution, organisms that can sense, move, and interact with their environment in ways unimaginable for their soft-bodied predecessors. Other Cambrian creatures were equally remarkable. Anomalocaris, a predator nearly a meter long, swam with grace, hunting smaller animals with specialized appendages. Hallucigenia, a spiny, worm-like organism, scuttled across the seafloor, its bizarre form defying comparison to modern animals. Opabenia, with its flexible trunk and 5 eyes, explored the sand in search of food. These creatures show that evolution was experimenting boldly, trying new forms, new strategies, and new ways to survive. The Cambrian Explosion also marked the rise of the first true ecosystems. Organisms occupied different niches. Some grazed on microbial mats, others filtered water, others hunted actively. Burrows, tunnels, and tracks in the sediment indicate complex interactions between species. The seafloor was no longer a barren stage. It was a dynamic, interactive environment. Imagine floating above a Cambrian reef. Trilobites move in patterns across the sand. Tiny arthropods scurry along the surface. Worms burrow below, and delicate sponges filter water overhead. Every movement, every feeding behavior, every interaction is part of a new web of life. These were the first recognizable ecosystems, a preview of the intricate relationships that would define life on Earth for hundreds of millions of years. The Cambrian Explosion was also a time of rapid innovation in body plans. Organisms experimented with symmetry, segmentation, appendages, eyes, and protective armor. These experiments produced the major lineages of animals that continue to this day. Many of the strange Cambrian creatures left no descendants, yet their innovations influenced evolutionary pathways. Predation, in particular, changed the rules of life. The emergence of hunters forced prey species to develop defenses, shells, spines, burrowing behaviors, and mobility. Life was no longer just about survival in isolation. It was about interaction, adaptation, and strategy. The ocean became a battleground, a classroom, and a laboratory, all at once. As you drift towards sleep, picture the Cambrian seas in your mind. The sunlight penetrates clear waters. The seafloor is alive with movement. Trilobites crawling, predators hunting, soft-bodied animals floating, sponges filtering water. Currents swirl gently, carrying nutrients, carrying life. The oceans hum with activity, yet all is calm, rhythmic, and mesmerizing. The Cambrian Explosion teaches us that evolution can accelerate, that complexity can arise rapidly when conditions allow, from invisible microbes to soft ediacaran forms, and now to hard-bodied, interactive animals. Life had entered a new era. The oceans were alive, diverse, and full of possibility, setting the stage for forests, coral reefs, insects, and eventually humans. For hundreds of millions of years, life thrived in the oceans. Plants, animals, and microbes had evolved complex strategies to survive, interact, and reproduce in watery environments. But eventually, a new frontier beckoned. The land, dry, exposed, and hostile at first, terrestrial environments presented challenges that were unlike anything life had faced before. Yet, life was ready for adventure. The first organisms to venture onto land were simple plants and fungi. Around 470 million years ago, tiny moss-like plants began to grow along damp shorelines and riverbanks. They clung to soil, rock, and sediments, soaking in water and nutrients. Fungi, too, appeared on land, forming symbiotic relationships with plants. These partnerships were crucial, as fungi helped plants absorb minerals and water from the soil, enabling them to thrive away from constant water sources. Imagine the landscape: low-lying rocks, streams meandering through soft soil, occasional pools of water reflecting sunlight. Tiny green pioneers cling to the moist surfaces, fragile but persistent. Wind rustles gently over the surfaces, and rain nourishes the first shoots. The air is thin, oxygen-rich, yet full of ultraviolet radiation, harsh to unprotected cells. Life adapts, learning to cope with dryness, sunlight, and the absence of constant water. Soon, arthropods followed. The first land animals were small, simple creatures, insects and relatives like millipedes and centipedes. They crawled over plants and soil, feeding on microbes, decaying matter, and each other. These early land animals were critical for shaping the terrestrial environment. Their movements aerated soil, distributed nutrients, and aided in the dispersal of plant spores. The conquest of land was not instantaneous. It took millions of years for plants and animals to establish themselves, to develop adaptations like cuticles to prevent water loss, structural tissues for support, and respiratory systems to extract oxygen from air rather than water. But each innovation allowed life to expand further inland, creating the first terrestrial ecosystems. By around 400 million years ago, more complex plants appeared. Early vascular plants developed structures like stems and roots, enabling them to grow taller and extract water more efficiently. Forests of primitive plants began to form along river valleys and wetlands, shading the ground and creating habitats for the first terrestrial animals. Early land animals also evolved remarkable adaptations. Arthropods developed exoskeletons to prevent desiccation and allow movement across dry surfaces. Some evolved primitive lungs or tracheal systems to breathe air directly. Life was beginning to master a new realm, gradually transforming deserts, riverbanks, and plains into living landscapes. The interaction between plants and animals was crucial. Plants provided food and shelter. Animals aided in reproduction, dispersing spores and seeds. Ecosystems began to develop layers: soil organisms below, plants above, herbivorous animals moving across surfaces, and predators following them. This was the first true terrestrial ecosystem, simple yet remarkably dynamic. As you drift toward sleep, imagine walking slowly through these ancient landscapes. Tiny green plants cling to rocks and soil, glistening after a rain. Millipede-like creatures crawl carefully, exploring the new terrain. The air is cool, filled with the scent of wet earth, sunlight filtering gently through mist. Every step, every breath Every rustle of life is a delicate dance between survival and adaptation. The movement of life from water to land was transformative. It reshaped the Earth's surface, altered atmospheric chemistry, and set the stage for forests, insects, amphibians, and eventually mammals. Life was no longer confined to oceans. It was expanding, exploring, and redefining the planet's possibilities. This period reminds us that evolution is patient and persistent. From tiny pioneering plants to small arthropods, life adapted, innovated, and overcame challenges that once seemed insurmountable. Earth, once dominated by oceans, was becoming a living mosaic of water, soil, plants, and animals. Around 420 million years ago, during the Silurian and Devonian periods, the oceans were alive with vertebrate diversity. Fish, the first vertebrates, had evolved jaws, fins, and scales, and they were exploring every ecological niche the seas offered. This era, often called the Age of Fishes, marks a remarkable expansion in complexity, behavior, and adaptation in aquatic life. Picture the seas. Sunlight filters through clear waters, illuminating vast reefs and swaying aquatic plants. Schools of jawless fish glide silently, feeding on microscopic organisms. Early armored fish, called placoderms, patrol the waters, their bony plates glinting in the sunlight. Among them, the first sharks appear, sleek and efficient predators, hunting smaller fish with agility and precision. Jawless fish, like lampreys and hagfish, represent ancient forms still surviving in modern times. But the evolution of jaws allowed fish to exploit new food sources. Predation, competition, and resource availability drove rapid diversification. Fish became active hunters, grazers, and scavengers, shaping the ocean's ecosystems in ways that echoed the Cambrian Explosion. Fins evolved into specialized forms. Paired fins allowed stability and maneuvering, while tail fins provided propulsion. Some fish developed armored plates for protection, while others remained soft-bodied and agile. Each adaptation was a solution to survival, a refinement of movement, defense, and predation. Reefs and shallow coastal waters became centers of biodiversity. Coral-like structures and microbial mats provided habitats for fish, invertebrates, and early predators. The oceans were dynamic, layered ecosystems where every organism influenced the others. Currents, tides, and waves carried nutrients, plankton, and juvenile fish across vast distances, creating interconnected habitats. The Devonian period, sometimes called the Age of Fishes, witnessed the rise of lobe-finned fish and early ray-finned fish. Lobe-finned fish are particularly important, as they would eventually give rise to the first tetrapods, the vertebrates that would move onto land. These fish had sturdy, muscular fins, capable of supporting weight in shallow waters, hinting at the first steps toward terrestrial locomotion. Imagine shallow Devonian estuaries. Lobe-finned fish crawl across muddy bottoms, navigating between plant roots and rocks. Small predators stalk them. Oxygen-rich waters support metabolism, growth, and reproduction. Currents swirl with plankton, carrying nutrients, while tides shape the sediment. Life is abundant, complex, and interactive, both predator and prey, adapting in a delicate balance. This period also saw the diversification of invertebrates. which played critical roles in the ecosystems. Early mollusks, arthropods, and echinoderms occupied the seafloor and midwater, providing food and competition for fish. The interplay of species drove innovation, armor, mobility, sensory organs, and behaviors evolved rapidly in response to environmental pressures. Fish were not only diversifying in the oceans, but also experimenting with shallow water habitats and estuaries. Here, interactions with terrestrial environments began. Fish navigated muddy banks, shallow pools, and flooded forests, encountering challenges that required adaptations in respiration and movement. These experiments would eventually lead to the first amphibians, the vertebrates that would permanently colonize land. As you drift toward sleep, imagine swimming alongside these ancient fish. Sunlight pierces the water in shifting patterns. Armored placoderms glide gracefully. Lobe-finned fish explore tidal pools, flexing their fins in ways that hint at walking. Currents carry plankton and nutrients through teeming reefs, while predators patrol and hunt. The oceans are alive, dynamic, and full of evolutionary experimentation. The Age of Fishes teaches us that innovation is continuous, from jaws to fins to predatory strategies. Life constantly explores new solutions to survival. These developments set the stage for life to expand further onto land, ultimately transforming Earth into a planet where vertebrates dominate both sea and land. The oceans remain central to life's story. They are the crucible in which vertebrate complexity emerges, the incubator for innovations that will echo for hundreds of millions of years. And within these ancient waters, the ancestors of all amphibians, reptiles, birds, and mammals, including humans, are already beginning to take shape. Around 370 million years ago, in the late Devonian period, the first vertebrates began a daring adventure, leaving the water to explore land. These early amphibians evolved from lobe-finned fish, whose sturdy fins were capable of supporting weight in shallow waters. The transition from aquatic to terrestrial life was slow, experimental, and remarkable, representing one of the greatest leaps in Earth's history. Imagine a shallow, muddy swamp, its waters teeming with lobe-finned fish. Over time, some begin to navigate the fringes, pushing through dense plant mats and across exposed mudflats. Their fins, muscular and flexible, allow short movements on land. Tiny lungs supplement gills, allowing these pioneers to extract oxygen directly from air. These are the ancestors of amphibians, bridging two worlds, water and land. Early amphibians were small, often under a meter in length. They retained some aquatic traits, such as tails for swimming, but their limbs were gradually adapting for walking on land. Their skin was thin and moist, allowing gas exchange, but requiring damp environments to prevent desiccation. Life on land was harsh, yet the advantages were irresistible. New food sources, fewer predators, and untapped ecological niches. These first amphibians fed on invertebrates, small arthropods, and other aquatic prey. They lived in swamps, marshes, and along riverbanks, where water remained close enough to sustain their skin and reproductive needs. Eggs were still laid in water, lacking the protective shells that later reptiles would develop. Life on land was limited but groundbreaking. The first steps toward the full colonization of terrestrial environments. The Devonian landscape was lush with primitive plants, moss-like greens, early vascular plants, and fern relatives. These plants stabilized soils, created microhabitats, and provided shelter and food for early amphibians. The world was quiet, save for the rustle of water, the gentle sway of plants in currents and wind, and the occasional movement of these pioneering vertebrates. Predation and survival shaped these amphibians. Some species became hunters, stalking insects and smaller aquatic organisms along the water's edge. Others remained cautious, retreating to water when danger approached. Natural selection favored adaptations that allowed movement, respiration, and sensory awareness in two environments simultaneously. Over millions of years, amphibians diversified. Some became more aquatic, refining swimming capabilities. Others became more terrestrial, improving limb strength, breathing, and coordination. The first lungs grew more efficient, and skin gradually developed glands to help maintain moisture. These adaptations allowed amphibians to exploit more distant terrestrial environments. Imagine walking slowly alongside a Devonian swamp. Mist rises from the water, sunlight filters through ancient ferns, and small amphibians crawl along mudflats. Their movements are deliberate, cautious, yet filled with purpose. Tiny eyes scan for predators, limbs flex with care, and the first echoes of terrestrial life resonate in the quiet world. The first amphibians are remarkable because they embody transition. They carry the heritage of fish and the potential for terrestrial life. Their journey would lead to reptiles, birds, mammals, and ultimately humans. They demonstrate that evolution often advances through gradual experimentation, trial and error, and adaptation to new opportunities. This period also marks the beginning of ecosystems that span water and land. Amphibians connect rivers, swamps, and terrestrial zones. Invertebrates and plants are interdependent, creating the first interconnected food webs between aquatic and terrestrial environments. Life is no longer confined to one domain. It is expanding, exploring, and shaping the world. As you drift toward sleep, picture these Devonian swamps. Mist rises from shallow waters. Small amphibians crawl carefully, testing the mud with their limbs. Plant mats sway gently, providing shade and shelter. Life is quiet, deliberate, and resilient. Learning to master two worlds at once, the first amphibians teach us patience and courage. From water to land, they explore new possibilities, demonstrating the power of adaptation and persistence. Their story is the bridge between oceans and continents, the foundation for the rich diversity of terrestrial life that will follow. Around 320 million years ago, during the late Carboniferous period, life on Earth reached another milestone. Reptiles emerged from their amphibian ancestors, evolving adaptations that allowed them to conquer dry land in ways amphibians could not. These early reptiles were small but resilient, carrying within them the potential for vast diversity, from towering dinosaurs to tiny lizards and birds that would one day take to the skies. Imagine dense, humid forests covering much of the land. Giant ferns, horsetails, and lycophytes tower overhead. Swamps and rivers are interwoven with drier plains. In this rich landscape, amphibians still thrive along water margins, but on firmer soil, The first reptiles scuttle with cautious determination, exploring habitats that were previously inaccessible. The defining feature of reptiles was the amniotic egg. Unlike amphibian eggs, which must remain in water, reptile eggs contained membranes and a shell, protecting the developing embryo from drying out. This allowed reptiles to reproduce entirely on land, freeing them from the constraints of swamps and streams. With this adaptation, reptiles could colonize forests, deserts, and uplands, expanding life's reach across the continents. Reptiles also developed thicker, scaly skin, which reduced water loss and provided protection from predators and harsh environmental conditions. Their limbs became stronger and more flexible, supporting movement over dry terrain. Lungs grew more efficient, allowing sustained activity on land. These adaptations allowed reptiles to thrive in environments that amphibians could only visit temporarily. The early Carboniferous world was rich in invertebrates, providing abundant food sources. Insects, millipedes, and other arthropods filled ecological niches, while primitive plants created shelter and microhabitats. Early reptiles hunted insects, small amphibians, and each other, establishing the first fully terrestrial food webs. Predation and competition drove rapid adaptation, shaping body size, speed, and sensory capabilities. One remarkable early reptile is Hylonomus, one of the first known reptiles. Small and agile, it navigated forest floors, hunting insects and avoiding predators. Its existence signals a major evolutionary breakthrough. Vertebrates could now thrive far from water, laying the groundwork for future terrestrial dominance. Reptiles diversified quickly. Some remained small, agile hunters, while others evolved heavier armor or specialized feeding adaptations. Ecosystems became more complex as reptiles occupied different niches, interacting with plants, invertebrates, amphibians, and each other. Life on land was no longer limited to the margins of water bodies. It now spanned forests, plains, and uplands. Imagine walking through a carboniferous forest. The air is humid, rich with the scent of plants and decaying matter. Small reptiles scuttle across fallen logs and leaf litter. Insects buzz nearby, and amphibians move cautiously along stream edges. The landscape is alive, layered, and interconnected, with life spreading across water and land in intricate, dynamic ways. The rise of reptiles set the stage for future evolutionary triumphs. With the amniotic egg, reptiles could exploit previously inaccessible habitats. Their success paved the way for the Age of Dinosaurs, the emergence of birds, and eventually mammals. Reptiles were not merely survivors. They were innovators, explorers, and architects of new ecosystems. As you drift toward sleep, imagine these early reptiles, small, nimble, alert, moving across a humid, fern-covered forest floor. Every step, every breath, every careful movement is a testament to adaptation and persistence. The earth is changing, landscapes are alive, and life continues to experiment, innovate, and thrive. The rise of reptiles teaches us that evolution can overcome limitations. From amphibians tethered to water, vertebrates evolved ways to conquer dry land, expand their habitats, and diversify in astonishing ways. Life was no longer constrained by the oceans or swamps. It was spreading across continents, bold, adaptable, and resilient. Around 299 million years ago, Earth entered the Permian period, a time of profound change. Reptiles continued to diversify. Plants spread across vast landscapes, and ecosystems became increasingly complex. Yet beneath the surface, forces were gathering that would test life in ways no species had ever experienced. This period would end with the most catastrophic extinction event in Earth's history, wiping out vast numbers of species and reshaping the course of evolution. The Permian world was dynamic and diverse. Vast continents merged into a supercontinent called Pangaea, stretching from pole to pole. Deserts expanded, mountains rose, and shallow seas receded. Forests of ferns, seed ferns, and early conifers covered the land. Reptiles, amphibians, and insects thrived in these varied environments. Rivers, lakes, and coastal areas were teeming with life. The oceans hosted fish, mollusks, corals, and brachiopods, forming complex marine ecosystems. Life seemed abundant, yet the Earth's environment was fragile. Volcanic activity increased in some regions, releasing gases that began to alter the climate. Temperature fluctuations stressed ecosystems. Sea levels rose and fell, shifting coastal habitats. Atmospheric composition changed over millions of years, sometimes limiting oxygen or altering carbon dioxide levels. These slow pressures were building silently, a prelude to catastrophe. Then came the End-Permian mass extinction, around 252 million years ago. It was the most severe extinction event Earth has ever experienced, erasing an estimated 90 to 96% of marine species and 70% of terrestrial species. Life on Earth was dramatically simplified, leaving empty niches, barren landscapes, and oceans nearly devoid of many previously dominant organisms. The causes of this mass extinction were complex. Massive volcanic eruptions in the region, now known as Siberia, released enormous quantities of carbon dioxide and methane, warming the climate. Ocean chemistry changed, leading to low oxygen levels in marine environments. Acidification and extreme temperatures stressed ecosystems, while widespread habitat loss left species vulnerable. Predation, competition, and disease further amplified the effects. Imagine the Permian Earth in the final stages. Forests shrink under heat and drought, rivers dry, leaving mudflats and salt pans. Oceans become sluggish, oxygen starved, and dotted with the remains of marine organisms. Reptiles and amphibians struggle to survive in extreme conditions. Life is fragile, struggling, yet the seeds for future diversity remain hidden in survivors. Some organisms persisted through this catastrophe. Certain reptiles, amphibians, insects, and microbial life found refuges in isolated habitats. Hardy plants survived in pockets of soil, and resilient marine species endured in deeper or oxygen-rich waters. These survivors would later radiate, repopulating Earth in the Triassic period and setting the stage for the rise of dinosaurs, mammals, and modern ecosystems. The Permian mass extinction teaches us about resilience and transformation. Life is vulnerable, yet persistent. Catastrophes do not end evolution, they reset it. They clear ecological space, challenge survivors to adapt, and create opportunities for innovation. From the ashes of the Permian, new life forms would emerge stronger, more diverse, and more specialized. As you drift toward sleep, Picture the late Permian Earth. Deserts stretch across Pangaea. Storms sweep through drying riverbeds. Small reptiles seek shelter under rocks and in shaded hollows. Tiny plants cling to soil patches, and resilient marine species linger in deep, oxygenated waters. Life is fragile, quiet, yet waiting, preparing for the next chapter. The Permian period and its mass extinction remind us that Earth is ever changing. Life endures, not by avoiding challenges, but by adapting, innovating, and persisting. From catastrophe arises opportunity, and from survival comes the foundation for future wonders. Around 230 million years ago, during the Triassic period, life began to recover from the catastrophic Permian extinction. Reptiles that survived the devastation diversified, exploring new habitats and ecological niches. Among them, a remarkable group evolved into the first true dinosaurs, creatures that would dominate terrestrial ecosystems for over 160 million years. Imagine the Triassic landscapes, sprawling plains, scattered forests of ferns and conifers, and rivers winding through valleys. The air is warm and humid, occasionally punctuated by storms. Small reptiles scuttle across the soil, insects buzz, and early amphibians linger near water sources. Among these creatures, early dinosaurs move cautiously, experimenting with bipedal locomotion, predation, and herbivory. Dinosaurs initially were small and nimble. Some were bipedal, moving swiftly on two legs, hunting insects or small vertebrates. Others were quadrupedal, browsing on plants or defending themselves with size and speed. Their lightweight skeletons, muscular limbs, and keen senses allowed them to explore environments inaccessible to other reptiles. Evolution was experimenting, creating a diversity of forms that would later include giants, flyers, and apex predators. The Triassic world was one of opportunity. Many ecological niches were empty due to the Permian extinction. Dinosaurs exploited these openings, diversifying rapidly. Early predators hunted small vertebrates, while herbivores grazed on abundant vegetation. Competition and predation drove further adaptation, shaping their bodies, behaviors, and social structures. Imagine floating over a Triassic plain. Small dinosaurs dart between ferns and tree ferns. Insects swarm, amphibians hop near streams, and early crocodile-like reptiles patrol riverbanks. The earth hums with life, quiet yet purposeful. Dinosaurs, still modest in size compared to their later descendants, move with intent, shaping the future of terrestrial ecosystems. By the late Triassic, some dinosaurs began to grow larger, developing specialized teeth for plant eating or sharp claws for hunting. Social behaviors likely emerged, with groups moving together for protection or hunting efficiency. Evolutionary experiments with posture, gait, and metabolism laid the foundation for the iconic diversity of the Jurassic and Cretaceous periods. The rise of dinosaurs also influenced other groups, mammal-like reptiles, insects, amphibians, and early plants all interacted with dinosaurs in complex ways. Predation, competition, and ecological balance shaped evolution on multiple levels. Ecosystems became increasingly interconnected, each species influencing the survival and behavior of others. As you drift toward sleep, imagine the Triassic Earth in motion. The sun warms sprawling plains. Small dinosaurs dart across fern-covered ground. Insects buzz and flit, Amphibians linger in puddles and streams. The wind rustles primitive conifers and ferns. Life is dynamic, balanced, and full of potential. These early dinosaurs are pioneers, exploring possibilities that will shape life for millions of years. The rise of dinosaurs teaches us about opportunity and adaptation. From the ruins of the Permian extinction, life recovered and innovated. Dinosaurs became masters of land, experimenting with size, form, and behavior. They remind us that even after devastation, life can flourish in astonishing ways. The age of dinosaurs spans the Jurassic and Cretaceous periods, from roughly 201 to 66 million years ago. During this time, dinosaurs evolved into a breathtaking diversity of forms, from towering giants to nimble hunters, shaping every terrestrial ecosystem. Meanwhile, the oceans were ruled by reptiles, skies were gradually filled by the first birds, and mammals remained small but persistent, quietly preparing for their own future. Imagine the Jurassic landscape. Vast conifer forests stretch across continents, ferns cover the ground, and rivers wind through fertile valleys. The air is warm and humid. Dinosaurs roam in herds and solitary hunts, moving across plains, climbing hills, and drinking from rivers. Their diversity is staggering. Long-necked sauropods graze treetops. Stegosaurs use plated backs for defense, and theropods hunt with agility and cunning. The oceans mirror this diversity. Ichthyosaurs glide gracefully through deep waters, while plesiosaurs patrol coastal regions with elongated necks and flippers. Mosasaurs, toward the end of the Cretaceous, become apex predators, demonstrating that evolution favors both specialization and adaptability. The seas are alive, a world of hunting, feeding, and survival, perfectly synchronized with the dynamics of land. The age of dinosaurs is also a time of evolutionary innovation. Birds emerge from small theropod dinosaurs, experimenting with feathers, flight, and complex behaviors. Mammals, though mostly small and nocturnal, begin to diversify in subtle ways, developing hair, more advanced teeth, and keen senses. Life is branching into niches more varied than ever before, preparing for the eventual dominance of mammals after the dinosaurs' decline. Imagine floating over a Cretaceous forest. Sauropods stretch high into trees, consuming leaves. Triceratops graze in herds, alert to approaching predators. Small feathered dinosaurs dart through underbrush, hunting insects or scavenging. Insects, mammals, and amphibians weave through plants and soil, creating intricate food webs. The air hums with life, every movement a testament to adaptation and survival. The age of dinosaurs is also marked by plate tectonics. Continents drift apart, creating shallow seas, mountain ranges, and new habitats. These geographical changes promote diversity, isolate populations, and drive evolution forward. Climate shifts, seasonal changes, and sea level fluctuations add pressure, further shaping life. Predation and defense reach new heights. Tyrannosaurus rex evolves powerful jaws, sharp teeth, and keen senses. Ankylosaurs develop armored bodies and tail clubs. Coevolution drives an evolutionary arms race, shaping morphology, behavior, and ecological roles. Every species influences others in complex and subtle ways. Despite their dominance, Dinosaurs were not eternal. By the end of the Cretaceous, around 66 million years ago, the Earth faced another catastrophic event. An asteroid impact and intensified volcanism triggered the Cretaceous Paleogene extinction, ending the reign of dinosaurs. Except for the lineage that gave rise to modern birds, life on Earth would once again be reset, giving mammals and other survivors the opportunity to expand and evolve. As you drift toward sleep, imagine the age of dinosaurs in vivid detail. Forests sway under a warm sun. Rivers sparkle with reflections. Giant sauropods move slowly. Theropods hunt silently. And small birds flit among ferns. Oceans pulse with life. From ichthyosaurs to mosasaurs, the world is dynamic, balanced, and alive. Every organism connected to the rhythms of its environment. The Age of Dinosaurs teaches us about adaptation, diversity, and resilience. Life flourishes in countless forms, from the massive to the minute, from the ocean depths to the treetops. Evolution is patient, experimental, and boundless. Even in a world dominated by giants, small organisms quietly prepare for the next chapter, ensuring that life continues its relentless journey. Around 66 million years ago, at the close of the Cretaceous period, Earth faced a monumental transformation. The asteroid impact and subsequent environmental upheavals ended the reign of non-avian dinosaurs, leaving vast landscapes and ecosystems empty. In the quiet aftermath, mammals and birds began to flourish, occupying niches once dominated by giants. This was the dawn of a new age, the Cenozoic era, often called the Age of Mammals. Imagine the early Paleocene landscapes. Forests gradually regrow across continents scarred by disaster. Rivers flow gently, lakes glimmer under the sun, and low-lying plants spread across fertile soils. Small mammals, previously nocturnal and inconspicuous, emerge boldly into daylight. They scurry across leaf litter, climb trees, burrow into soil, and explore every ecological opportunity. Life is tentative, yet filled with possibility. Mammals diversified rapidly. Rodent-like creatures evolve, omnivorous and adaptable, while early primates begin to climb trees, developing grasping hands and acute vision. Some grow larger, becoming herbivores or predators. Teeth specialize for diet. Limbs adapt for running, climbing, or digging. Evolution experiments with form, behavior, and intelligence, shaping the mammals that will dominate in millions of years. Meanwhile, birds, descendants of small theropod dinosaurs, radiate across skies and forests. They develop flight, feathers, and complex behaviors, exploiting niches from aerial hunting to seed dispersal. Early birds experiment with size, beak shape, and habitat, becoming crucial parts of ecosystems. Their song, flight, and migration patterns begin to reshape interactions between plants, insects, and other animals. Imagine gliding over a recovering post-Cretaceous forest. Mammals explore underbrush and treetops. Birds swoop through canopy gaps, searching for insects and seeds. Insects, amphibians, and reptiles fill other layers of the environment. Life hums softly, interconnected, and dynamic. Every movement, every feeding, every breath contributes to the rebuilding of Earth's web of life. The Cenozoic era also witnesses dramatic climate and geological changes. Continents drift to their current positions. Mountain ranges rise, rivers carve valleys, and grasslands expand. Climate shifts create deserts, savannas, and temperate forests, offering diverse habitats. Mammals adapt. Hooved herbivores roam open plains. Predators evolve speed and strategy, and small mammals explore underground and arboreal niches. Predation and competition drive innovation. Carnivorous mammals develop sharp teeth, claws, and keen senses. Herbivores evolve grinding teeth, complex digestive systems, and herd behaviors. Birds refine flight, migration, and foraging strategies. Each species influences others in subtle ways, weaving complex ecological networks that mirror the balance seen in dinosaur ecosystems. But with mammals and birds now at the center, during this time, early primates evolve important adaptations, grasping hands, stereoscopic vision, and flexible limbs. They occupy trees, forage for fruits and insects, and navigate three-dimensional habitats with skill and curiosity. These small, agile creatures are the distant ancestors of humans, quietly setting the stage for future intelligence and culture. As you drift toward sleep, picture a Cenozoic landscape. Forests stretch across continents, rivers shimmer, birds flit between branches, and mammals roam, hunt, and forage. The earth is recovering, alive with innovation, diversity, and quiet energy. Life is resilient, experimenting in countless forms, preparing for the richness yet to come. The rise of mammals and birds teaches us about persistence and opportunity. From the shadows of extinction, small adaptable survivors grow, diversify, and thrive. Life, patient and inventive, reshapes ecosystems, filling voids left by giants and creating new patterns of survival and interaction. The world is alive, dynamic, and endlessly inventive, carrying forward the legacy of millions of years of evolution. Around 2.6 million years ago, Earth entered the Quaternary period, marked by a series of ice ages. Massive glaciers expanded across continents, covering much of North America, Europe, and Asia. Sea levels dropped as water became locked in ice, and climate fluctuated between cold glacial periods and warmer interglacial intervals. These cycles profoundly influenced life, shaping ecosystems and driving evolution. Imagine the landscape during an ice age. Snow and ice dominate northern continents. Glaciers carve valleys, and tundra spreads across plains. Rivers flow from melting ice sheets, and winds carry frigid air. Life adapts to extreme conditions. Mammoths roam grassy plains. Giant ground sloths forage in forests, and small mammals burrow to escape the cold. Vegetation shifts with climate, with conifers, grasses, and tundra plants replacing once lush forests. Among these mammals, a new lineage is quietly emerging, primates that will eventually give rise to humans. Early hominins evolve in Africa, adapting to savannas, woodlands, and varied terrains. Bipedalism develops, freeing hands for tool use. Teeth and jaws adapt to diverse diets, and brain size gradually increases. These adaptations allow early humans to survive, explore, and innovate in challenging environments. The ice ages also drive migration. Humans and other animals move to follow food sources, adapt to new climates, and colonize new continents. Land bridges, such as the Bering Strait, allow species to cross oceans of ice and water, spreading life across the globe. These migrations create genetic diversity, fostering adaptation and resilience in changing environments. Imagine walking across an African savanna 2 million years ago. Early hominins move cautiously through tall grasses. Large herbivores graze nearby. The air is warm but dry. Sounds of birds, insects, and distant predators fill the landscape. Life is dynamic, challenging, and full of opportunity. Small groups of humans begin to hunt, gather, and learn to cooperate, laying the foundations of culture, community, and survival. Over hundreds of thousands of years, humans develop tools, fire, and complex social structures. They learn to hunt cooperatively, store food, and protect themselves from predators. Language and communication evolve, allowing knowledge to pass between generations. Each innovation increases survival, fosters exploration, and sets the stage for the modern world. The repeated ice ages challenge life in other ways. Glacial advances destroy habitats, forcing species to migrate or adapt. Warming periods allow forests and grasslands to expand. This constant fluctuation drives evolution, favoring flexibility, intelligence, and resilience. Species that cannot adapt perish, while survivors diversify and explore new niches. Humans eventually spread beyond Africa, reaching Europe, Asia, the Americas, and Australia. They encounter diverse climates, animals, and ecosystems. Each region presents unique challenges, shaping culture, technology, and adaptation. Humans learn to hunt megafauna, cultivate plants, and create tools and shelters, mastering the environment in ways no other species has before. As you drift towards sleep, picture Earth during the ice ages. Glaciers carve mountains, snow blankets vast plains. Mammoths, bison, and giant sloths roam the tundra. Early humans move cautiously, foraging, hunting, and exploring. Life is harsh, but persistent, full of adaptation, ingenuity, and quiet determination. Every breath, every movement, every survival story contributes to the unfolding tapestry of life. The ice ages and human evolution teach us about resilience, creativity, and adaptation. Life faces extreme challenges, yet through intelligence, cooperation, and persistence, it continues to thrive. Humans, emerging from this harsh world, carry forward millions of years of evolution, ready to shape the planet in ways both wondrous and profound. The story of Earth continues into the Holocene epoch, beginning around 11,700 years ago, after the last major ice age. As glaciers retreated, climates stabilized, and ecosystems flourished. Forests expanded, rivers meandered peacefully, and grasslands spread. Humans, now skilled hunters and gatherers, began shaping their environments in subtle but profound ways. Agriculture emerged, settlements grew, and the foundations of civilization were laid. Imagine early river valleys, fertile soils, abundant water, and rich vegetation. Early humans plant crops, tend animals, and build simple structures. Forests provide wood for fires and shelters. Rivers supply fish and water, and animals roam freely. Life is balanced, ecosystems are intact, and humans live in close connection with the rhythms of the natural world. Over millennia, human populations grow and spread across continents. Agriculture allows the rise of villages, towns, and eventually cities. Trade networks emerge, knowledge accumulates, passed from generation to generation. With growing technology, humans begin to alter landscapes more deliberately. Forests are cleared for fields, rivers are dammed, and species are domesticated. Earth begins to bear the visible marks of human activity. The Industrial Revolution, beginning around 250 years ago, accelerates human impact dramatically. Fossil fuels power machines, cities expand, and technology reshapes transportation, communication, and agriculture, while human ingenuity allows unprecedented growth and prosperity. It also imposes new pressures on the natural world: habitat loss, pollution, climate change, and species extinction. Modern ecosystems are now a complex blend of natural and human-influenced landscapes. Forests, oceans, deserts, and wetlands still harbor incredible biodiversity. Mammals, birds, insects, fish, and plants continue to adapt and evolve. Yet humans now play a central role in shaping habitats, species distributions, and ecological processes. Conservation efforts aim to protect species, restore habitats, and mitigate human-induced changes, highlighting the delicate balance between life and human activity. Imagine Earth today from a quiet perspective. Mountains rise, rivers flow, oceans ripple with life, and forests sway in the wind. Cities hum with human activity, yet natural landscapes persist nearby. Species adapt to coexist with humans, some thriving in urban spaces, others remaining in wilderness refuges. Life continues its intricate dance, dynamic, resilient, and ever-changing. Modern Earth teaches us about responsibility and interconnectedness. Humans are now stewards of the planet, capable of both destruction and restoration. Our actions influence climate, ecosystems, and species survival. Yet this influence also carries opportunity to understand, protect, and nurture the web of life that has evolved over billions of years. As you drift toward sleep, imagine a calm view of modern Earth. Oceans shimmer with sunlight, forests sway gently, rivers glimmer and flow, and wildlife moves quietly across diverse landscapes. Human communities exist in harmony with nature, learning from and adapting to the environment. Life pulses with resilience, continuity, and possibility, connecting the past, present, and future in a timeless rhythm. The story of modern Earth and human impact reminds us that life is ongoing, dynamic, and fragile, yet capable of remarkable adaptation and innovation. From the first single-celled organisms to humans shaping the planet, the journey of life continues, resilient and profound, inviting us to participate responsibly in its next chapters. Now, with a smile on your face, you will have a good understanding of the history of our Earth, and hopefully, a good night's sleep. Goodbye, dear friend. See you next time.